bad, but what can you do?
Yeah.
Okay, so Verus is not here yet, right?
Right, and Jorge.
And Jorge is not here yet, but the young one is here. I can see you.
Oh.
Hi. Yeah, so let's wait for a couple of, well, 1 minute, hopefully.
Sure.
Karen wanted to say hi too.
Oh, hi, Mom.
Hi. Hi.
Hi.
Thanks everybody for being Tor's family away from home for the last 5 years.
Yeah.
And where are the parents dialing from?
Minnesota,
Oh,
Minneapolis.
wow.
It's kind of nice, actually. The format that we're forced into makes the attendance a lot easier for them.
Yep.
Yeah.
So I see
Yeah.
Beiruz is in here now. Hi,
Hey.
Beiruz.
Hey, how are you doing?
Good.
Hi, Verus.
Hi, Sonia. Hi, Miroslav.
Hey, Bruce.
How are you doing?
Pretty good, pretty good. I've been hearing your name mentioned with regards to some efforts to start organizing the community that works on COVID, especially on the systems and signals and estimation efforts on our campus, which is probably quite sizable in the form of some seminars, workshops, and so on. I don't know if this is progressing, but Tara shared this with Sandy Brown and me, and we were delighted.
Okay, yeah, we're doing something. I don't know. We're trying our best. We're trying to model using dynamics and some stochastic stuff.
Yeah, we're in the shadows of the people who do biology, work in labs, take measurements. And what you guys do is, in some ways, orders of magnitude. It's more sophisticated, but it's not getting any press as the other things.
Well, yeah, I mean, it's a in progress thing. I'm afraid it's going to be ready after the vaccine is done.
For the next pandemic, so.
And for the next pandemic, it might be ready.
Exactly.
But we're doing something in the dynamics, stochastic dynamics side, trying to do the system ID.
So
Okay.
in terms of committee members, I think we're still just waiting on
Yeah.
Jorge, but maybe
Jorge
I can.
is there.
Oh,
I
he
can see
joined.
him.
Great. Welcome. Okay,
Yes.
everyone's here.
So, yes, everyone's here. So I would like to welcome everyone and thank you for attending Tor's presentation on his dissertation work. It's been some time since he started, but we are finally here. So so let's hear what he has to tell us about. And so before we start, I would like to mention that for the presentation, to make it as smooth as possible, I will allow only for some interactions that have to, help you clarify things. But I'll stop you, or I'll stop the discussion if it's lingering for too long. So so that you can, it's better that you ask your questions at the end of the presentation. Okay, so let's get them started. Tor is going to talk about distributed Newton-like algorithms and learning for optimized power dispatch. Okay, Tor, so the floor is yours.
Yeah, so thank you, Sonia, for the introduction. So based on the title of this talk, for those of you in here who don't really know what you got yourself into, you can kind of expect a very mathematical type of talk where we'll see some algorithm statements that are in the form of differential equations or discrete updates in sort of a dynamical system sense. So for those who aren't as technically familiar with these types of things, I'll try to kind of walk through, some intuition for these types of algorithms, but just know what you're getting into here. And so I'll start with just a brief high-level sort of real-world motivation for the types of problems and algorithms that I'm going to be discussing. And so in renewable energy applications, as the penetration of renewable resources is increasing, we find ourselves moving from this sort of vertical top-down type of paradigm that you see on the left-hand side of that bottom image here, over towards more of a flat horizontal type of paradigm where we're introducing possibly many more generators into the system that are more decentralized by nature. And so this makes real-time power dispatch a lot more challenging for independent service operators. In particular, they're looking to meet some load constraint in real time, and they would like to use the cheapest or the greenest possible energy. But these types of optimization problems that they're facing are becoming more and more difficult to do in real time. And so that's the motivation for developing powerful algorithms to assist this. And so here's the outline of the talk. It's going to be broken roughly into two parts, but majority of the time on part one, and then time permitting, I'll talk about a couple additional topics. And so in particular in part one, we're going to be covering distributed resource allocation type of problems. And I'll talk about 3 cases of that, and then 3 classes of algorithms that we have developed for each case. So starting here first with the convex case, we're going to consider a problem formulation that I call economic dispatch, the basic form of it. And basically what we're looking at here is just that we have a set of N generators or possibly flexible loads that can modulate their power production or consumption. And we want to satisfy some global load constraints. So you'll see that in the constraints down at the bottom there, subject to this equality constraint, which introduces sort of a global nature to this problem. And then additionally, we'll subject these generators to box constraints so they can only produce or consume a minimum or maximum amount. And so the solution approach we're going to be looking at here sort of looks like this. We're going to be interested in the cyber layer of this network, where these generators are each modeled as agents in a system that can exchange some messages only with a few other agents in the system. And so that's sort of, the type of algorithm that we're looking to develop so that they can collectively determine the solution to this problem. So a brief overview of what's been done here. Majority of literature on this type of stuff is about gradient-based methods, or at least, those are the most mature and well-studied approaches to problems like this. So there are some Newton-based methods that have started to mature, particularly over the last decade or so. But in many cases, they actually don't scale particularly well, in the sense that the information that's required to be exchanged actually grows with the network size in some cases. And they typically do not address these box constraints that I introduced on the previous slide that we're interested in satisfying. And then as far as edge weight design goes, I'm going to just very briefly touch on that probably towards the end. But we're interested, another contribution of this work is designing weightings for the communication links between agents that is motivated more from a Newton-like or second order perspective. And so what is our sort of high level approach going to look like? Well, first, if we look at the centralized Newton descent method for unconstrained optimization, we have that this inverse of a Hessian matrix pops up. And so the Hessian matrix being a matrix filled with second derivatives of the function. This might be sparse, meaning it has many entries equal to 0 in a distributed application, but the inverse of a sparse matrix is not necessarily sparse. And sparsity is sort of required in distributed applications so that when we do our matrix operations that we're not requiring information from the entire network. So we have to figure out sort of a new notion for inverting this Hessian matrix. And then also, how do we actually deal with that global constraint and the box constraints? And so then our approach to this is we'll reformulate that EDPB problem that I showed a few slides ago via the Laplacian matrix to eliminate that global constraint. And then we'll use a Taylor series expansion to compute an approximation of this matrix inverse. And that, you know, sort of endows the distributed nature into the architecture. So we'll talk about two algorithms here, what I call Dana R for the relaxed box constraint case. This is a discrete time algorithm, but we don't consider the box constraints in this case. And then Dana B for the box constraint case. This will be a continuous time algorithm, but it's suited only for cost functions that are nearly quadratic, so to speak. And then finally, we have, you know, a convex approximation for this weight design problem. I'll just touch on that briefly at the end. So first step here is to introduce the Laplacian matrix. And importantly, the Laplacian matrix, if the graph is connected, has the property that its null space is the span of ones. And so if we introduce then an initial condition which satisfies the global load constraint, then we can show that stepping in the image of the Laplacian via a new variable will make it so that we still satisfy that global load constraint. And that's seen just very straightforwardly from multiplying by the left by vector of all ones and then applying that null space property. So then what's our reformulation of that problem that I showed earlier? Well, we have a new problem now, which is an optimization in Z. And so in particular, you know, we have this new function g of z, which is just the same as f, but evaluated in sort of our new variable subspace. And then the box constraints look a little different, but that global constraint is completely eliminated just because we're only stepping in the image of that Laplacian. So here, sort of moving forward into what our approach for solving that EDPL problem will be. Well, we recall this Taylor series expansion generally for a matrix A who has eigenvalues that are bounded in some sense. Then we can compute via an infinite series, its inverse. And so what you see here in the AQ definition of this AQ matrix is just a finite sum of this identity minus LHL. That LHL matrix is the Hessian of this reformulated problem, where the L's show up just due to some chain rule, and the H is the Hessian of the original problem. And then in particular, we'll consider this Z Newton step where we just have this AQ matrix, which now is sort of our Hessian inverse approximation, and then we multiply that by the gradient. And so in particular, you know, the edge weighting, just to briefly touch on that, is related to satisfying this requirement that the matrix needs to have bounded eigenvalues in some sense. And so then what's our algorithm going to look like for this? Well, it's basically just very similar to the centralized case. Remember, we've relaxed these box constraints. So now we're just taking new Newton steps only in the image of that Laplacian matrix. And then this AQ matrix, you know, has some distributed sparse structure. Okay, so what are some theoretical results on this? Well, first of all, we have just some standard assumptions, including, you know, strongly convex local costs. We've bounded the eigenvalues of this matrix so that they're contained in the unit ball, except for the one that's fixed at 1. That's okay, just due to the null space of the Laplacian. And we have this bound on our step size alpha that showed up, you know, in our algorithm statement. And so then first we'll just establish that this algorithm asymptotically converges to the solution. So we'll just consider solutions in terms of Z star, where you can compute then the solution to the original primal variable X via this update using Z star, right? And so then the keys to the analysis on this are, it's just sort of Lyapunov function based, some observations about these trajectories in Z, and reasoning with doing some algebraic manipulation of this AQ matrix. And then that gives us a bound on alpha, our step size. So next, the result on the same algorithm, the previous result was that we converge asymptotically, but actually we can say something a little better, which is if we choose an alpha, in particular the one that is halfway between the bounds that I showed before for the alpha, then we converge linearly in this sense. So there's a nasty expression in terms of epsilon, q, and n here. And I'll just briefly note that this expression does monotonically improve for when you squeeze epsilon tighter. If epsilon is very small, the intuition is that our approximations to the Hessian inverse are more accurate, so we actually do better. And it also improves for increasing q, which is the number of terms that we use for that AQ matrix. So keys to this proof, sort of borrowing results from the previous proof and then just computing these terms explicitly and bounding where we need to and substituting this particular choice of alpha. So now we'll talk about a continuous time version of this algorithm for the full box constraint. So all we're doing here is pretty much taking the very similar primal dynamics, but now in continuous time. And actually a better way to look at this is it's just a modification on a traditional saddle point method. So lambda here, is a dual variable associated with those box constraints that we had before. And now, our z dot, the difference between this and the traditional saddle point dynamics is we have this AQ matrix in here, which gives us that second order flavor. And so what's our result here? Well, we have pretty much the same set of assumptions, except now we need to additionally consider that these local costs are quadratic so that their second derivatives are fixed. And then what we obtain is that we asymptotically converge to the solution z star lambda star under these dynamics. And again, there's some reasoning with epsilon and q. You can show that you'll actually do better by just examining the modes of the dynamics. And so the keys to this are, again, we can use Lyapunov to establish convergence to the z star. That doesn't quite get us to lambda star, so we have some tricks to handle these non-smooth projection dynamics that I showed on the previous slide. And then reasoning with KKT conditions and LaSalle to obtain that lambda star convergence. And so one thing to note is just by appealing to continuity, we actually get that this still converges for nearly quadratic costs in the sense that their Hessian or second derivatives can deviate a little bit. And the zeta might need to be arbitrarily small, but that's just an appeal to continuity there. So just briefly kind of visualizing the trajectories of this thing for various q. So what we notice here is q equals 0 is analogous to a gradient type of method. And so this one sort of unsurprisingly performs the worst here, where each marking that you're seeing on the plots is 0.2 seconds of continuous time algorithm time. And so you see the gradient method kind of circles around the constrained optimizer here. By the way, if I didn't mention, what we're looking at is a 3-node case, but I've projected the level sets and the box constraints onto the 2D plane where that equality constraint is satisfied. And so we also notice some qualitatively different behavior of even q versus odd q. And that actually kind of shows up in the analysis here, but you'll notice Q2, 4, and 6 kind of are similar shape to the gradient trajectory, while Q1, 3, 5 sort of overshoot the optimizer and then get wrangled back in. This kind of shows up in the analysis, so I'll just kind of point that out and leave it there for now. So for the relaxed problem case, we do better and better as we increase q, and in particular, even our analogous gradient type of method, q equals 0, outperforms traditional distributed gradient, and that's just by virtue of having weighted our Laplacian using a second order approach. So that's the main difference there, why we can actually just via that weighting, we can still implement gradient and outperform more traditional methods. So for the continuous time algorithm in the box constraint case, we notice, the convergence is clearly not so linear. And there's something a little interesting going on here with Qs. We no longer do monotonically better as we increase Q. Particularly if you look at the orange and the yellow line for Q equal 4 and 5, Q4 actually does a little bit better than Q equals 5. So again, this kind of shows up in the analysis, but I'll kind of leave it there for now. So finally, an additional contribution on this work was that we formulated this design of the edge weights of the Laplacian in order to try to minimize that epsilon parameter as much as possible. This is a bilinear non-convex optimization, but we obtained a convex approximation to it, and we can guarantee that we get that unit ball bounding that we need. So we have a couple publications on this. Future directions, designing for robustness. We speculate that it's possible we actually can get around that initial condition requirement by an extra Lagrange term. And so we've done some simulations on this. The analysis is actually not trivial there. There's some extra steps definitely that are required. But that seems to work, in simulation. And then some other improvements, for example, just introducing second order type dynamics for that dual variable. Okay. And so moving on to the second topic here, we're going to consider what I refer to as a nested stochastic case. So what is going on here? Well, I'll start out with sort of a motivating example. If we consider a system of electric vehicle users, where each of them possibly, has some charging preferences for their electric vehicle, and also they have solar PV generators. And so, the goal of this system is we want to sort of balance the charging with the solar output, which is fairly easy in case A, where we might expect, sunny weather, and then the solar is deterministic, but becomes much more complicated in case B, where possibly there's some intermittent cloud coverage, and therefore, the PV generation is modeled as some stochastic amount. And so then, if we think about, well, possibly we can incentivize these users to step down their charging depending on, what the realization of solar energy is at any moment in time. How do we sort of optimally incentivize them to do this? And so the model is going to look like this. What we're looking at is two optimization problems here, an outer problem, OP, and an inner problem, IP. So let's start with IP because it's a little simpler. So in the case of IP, just consider that chi, which shows up in that constraint there, is some fixed realization over some distribution. So for the sake of solving this problem, we consider it a deterministic value that has already been realized. And so then this just looks very similar to our previous problem that we looked at, where we're just trying to meet this load constraint. We've removed the box constraints in this case. But we have some interaction with a design variable x. And so, again, for each instance of IP, x would just be some fixed value. And then for, oh, my dog is maybe saying hi to us. Okay. So for the outer problem, then what we're trying to do is minimize the expected optimal cost of realizing, instances of this inner problem. So that's where I've sort of defined this f chi to be equivalent to the optimal cost of that inner problem. And so in particular, we want to develop, this optimal, so x in this case would be appealing to that example, would be like the incentive that we're trying to design or learn. And so we want to solve possibly some instances of the inner problem to construct the solution for the outer problem. And in particular, we want to solve very few of those if we can, because it's expensive to repeatedly solve optimization problems. Okay, so just a brief note on the literature then. What we're going to consider is a method that looks sort of like the classical cubic regularized Newton method. And so, so there's a lot of work that has been done on these types of methods in the last 5 years or so. But in particular, very few works in the literature actually consider distributed approaches. And that's because we have sort of a wrench thrown into things with this regularization term there, the x minus xk cubed. That's sort of a global term that's difficult to compute in a distributed setting. The only distributed work that I'm even aware of on this is this Uribe and Jad Babai paper, which is a preprint and is only limited to convex settings. And so, we're going to try to come up with an approach that unites distributed, stochastic, and non-convex elements for this. So what's our goal? Well, we want to obtain a subsolver for this inner problem, which in particular will terminate in finite time, if possible, because we don't want to be running these things all the way to convergence every time. And then how do we actually obtain distributed cubic regularized updates to that outer problem? So the high-level approach here is we'll just consider some very simple Laplacian-gradient-based subsolver dynamics for the inner problem. But this will assist in, sort of accommodating a finite time solver, and you'll see that maybe in a moment. And then we'll formulate a distributed cubic submodel for the outer problem so that we can compute that update over a distributed network. And so then really what we're going to be doing to obtain those outer problem updates is using batches of approximate inner problem solutions. And so we'll get into that, in terms of when the algorithm statement is coming up here. So the contributions here are we develop a stopping criterion for these inner problems using that Laplacian gradient-based subsolver, which can be determined distributedly. And then those approximate solutions are directly leveraged in the analysis for the convergence of our DISCRN algorithm. Distributed Stochastic Cubic Regularized Newton is the acronym there. And that's used for solving the outer problem. So this will be very non-alarming to any people who are familiar with algorithms here. So we just consider basic Laplacian gradient-based subsolver. So we have some propositions about this. So in particular, maybe I hadn't mentioned yet, but F, we assume is strongly convex in P, but not necessarily in X. It could be non-convex in X. And so here are, just some basic assumptions. And in particular, propositions 1 and 2, again, I would say are probably non-alarming. We just have asymptotic convergence of this basic subsolver, asymptotic and exponential, actually, if you pick a particular step size. But we do actually go through the legwork of proving these just because we use them, the results of those proofs in our development of this distributed stopping criterion, which is in proposition 3 here. And so in particular, what agents can do to determine that their updates are close enough in the sense of this delta constant that you see in proposition 3 there, is they determine, as their updates get smaller and smaller, if the update pi plus minus pi is small enough, then the agents, and that holds true for the entire network, then the agents know that they're close enough to the true optimizer p star in the sense of delta. And so, nothing too surprising with the analysis going on here, just some algebraic manipulations to get to that proposition 3. Okay, so then what is actually our DISCRN update, this distributed cubic submodel for the outer problem? We're going to consider, something similar to the classical submodel, except for the key difference here is, well, 2 key differences. First of all, we're considering only, batches of solutions in order to determine our gradient GK and HK. So this is sort of more of like an empirical risk type of approach. And then we separate those cubic regularized terms into so that each agent is just determining, its regularization from a local perspective. And so that gets us, the key distributed structure that we need. So the goal is then just to compute for the update to our outer problem, a minimizer of this cubic submodel such that the agents agree on that minimizer, this consensus constraint. And a method that you can use for this, a pretty recent paper actually that was sort of justifying that these dynamics converge with some nice properties for the non-convex case. And so we consider decentralized non-convex gradient descent as sort of a subsolver to obtain that update. And so you'll notice, here the superscript on X has a plus, and that's because we're trying to find out what is the X plus that we'd like to obtain. And then we're iterating only in t here, right? So t plus 1 is on the left-hand side of that equation. Okay. So here we'll get to the statement of what is this DISCRN algorithm. So you'll notice 5 steps here. Steps 1 through 3 are related to solving instances of the inner loop, or rather of the inner problem. So this could be considered like the inner loop of our full DISCRN algorithm. And then, once we've done steps 1 through 3, we have a full batch and we're prepared to compute an update to that outer problem. And so we do that in steps 4 and 5. We just determine what the locally required elements are of the gradient and Hessian based on these sort of realizations of those inner problems. And then we compute an update to the cubic submodel, which might be challenging. So we actually need that update just to satisfy some condition, which I'll talk about briefly on the next slide. And then we repeat from step 1. And so what are the conditions that we need for this thing to converge? Well, I've really boiled down a lot of them here. So I have a slide in the appendix here, which has a lot more symbols on the page, if you can believe that, and is much more densely packed. But for now, we can just kind of consider, okay, there's some standard assumptions related to graph connectivity, Lipschitzness, bounded variance. We need that our batch size is big enough. And that's related to this constant C, which is related to condition 1 here. And so in particular, we do need that these updates satisfy that they are at some consensus position. Although we can justify in simulation that possibly this isn't actually required. But for now, the analysis requires this. And then also, that the updates either reduce the cubic submodel and the function value, or are not too large in some, on the order of C sense. And so we can actually say in the centralized case that gradient descent does satisfy that condition 2, or rather part 2 of condition 1. And so then what is actually the result? Well, we get that each, local copy of the state asymptotically converges to the same epsilon second order stationary point with some probability related to zeta. And again, zeta showed up in our batch size requirement on the previous slide. So the keys here are just doing some bounding on the gradient and Hessian errors using Jensen's inequality, which is sort of a tool in stochastic analysis of these stochastic optimizations. And then also we apply this cross Lipschitz assumption. And so this is sort of a non-standard thing, but by that I mean, by cross Lipschitz, if we change P a little bit, then the gradient and Hessians with respect to X only change a little bit. And that's crucial so that we can actually accommodate approximate solutions to the inner problem. And so we build on, something that was recently appeared in literature on that. Okay, so what are the simulations here? Well, we have some very encouraging results, which is that we sort of bend the corner here. In this case, well, let me first talk about the cost functions. I choose a very non-convex case here. So the alpha i's are quartic, and in particular, they're non-convex quartics. So they have 2 isolated local minima. And then, quadratic beta i's. So these make up the coefficients of what is then a quadratic cost function in P sub I. And so then to get back to the plot, we notice that we start bending the corner after around 10 outer loop updates. And remember, each outer loop update, because our batch size is 20, requires that we solve 20 instances of the inner problem up to an accuracy of delta equals 0.1 in this case. So it's really good that we have substantially improved over the analogous gradient and Newton-based type of approaches to this. And again, we can accommodate actually some, small non-zero disagreement without observing destabilization in this case. So that's encouraging. So there's a report being prepared on this, and some future directions, or rather, is under revision right now. And future directions on this are, in particular, I'd really like to extend it to accommodate some small disagreements in those agent states. So I have some more technical thoughts on that, but I'll leave it there for now. And then, convergence rate and adaptive batch size techniques are also interesting. Saddle point dynamics, if you're interested in getting those dual variables for free, that might be beneficial. Okay, So now moving on to the third main topic that we'll be considering here is a binary case. We're going to revert a bit more back to the previous convex case in terms of we don't consider a nested or stochastic elements here. And so what does this binary case look like? Well, we'll consider that we have devices where before we allowed them to operate on some continuous interval between a minimum and maximum amount, but now we require that they actually just operate in an on or off state. And so there's some incremental cost of operating in the on state versus the off state. And instead of imposing the global matching constraint as an actual constraint in the optimization, we include it as a penalty term instead. And the reason for that is you might suspect this looks sort of like a knapsack problem. We might run into some trouble if there doesn't exist a permutation of on-off states that actually exactly meet the load requirement. So we'll just try to get as close to it as possible. And so you might be wondering why I've included a picture of a brain network here and then, you know, pointing to this sigmoidal type function. And the reason for that is we're going to use sort of a neural network type of approach here, where in particular we'll benefit from properties of this sigmoidal function in that, you know, we're looking at a 0-1 optimization scenario here. And so we can sort of hearken to activations of neuron potentials, which are typically modeled using these sigmoidal functions where, you know, given any real number, we can map, you know, the entire real line onto the interval between 0 and 1 using sigmoidal functions. And this is a very common type of approach in neural networks. But one key difference in our approach versus what you might be more used to seeing in the neural network approach is that we obtain our neural weights, W, and biases directly from the problem data. So in particular, if we choose to model this just as a quadratic optimization, remember we can pick, you know, some family of coefficients AI and BI here, as long as we're satisfying, you know, the requirement that operating in the 1 state versus operating in the 0 state has this incremental cost CI. So we have some freedom in those AIs and BIs. And so then we obtain, you know, just from the problem data, these neural weight and bias matrices. So you'll notice here that this W is fully populated, and that's something that we'll try to work around shortly here. So let's briefly just talk about what is standard here. I'd say, you know, the first gut instinct on problems like this would be either a greedy type of approach or an SDP relaxation type of approach. And what both of these suffer from is they're centralized. There's really, you know, it's difficult to kind of get around that requirement that you need data about the entire problem, the whole network, in order to compute either an SDP relaxation or a greedy update. And in particular, SDPs scale very poorly. You know, they become very expensive to compute when the network size grows. So we want a method that is more scalable than that. And so we'll build on these hop field neural network approach, which is, by the way, vulnerable to saddle points and is non-distributed in sort of the way that it exists currently in the literature. So I'll talk about that in particular a bit more on this slide here. So our goal is to develop a distributed solver for this binary economic dispatch. The all-to-all hop field dynamics is going to be a problem for us. We have to figure out how to distribute those. And in particular, hop field neural network dynamics, which I haven't really discussed too much, but I'll get to shortly, are susceptible to saddle points. And that's because it sort of looks like gradient descent, you can think of, on an associated energy function. And so, you know, Newton-like approaches benefit from sort of repelling you from those slow converging manifolds that saddle points induce in the state space. And so what is, you know, then our high level approach? Of course, we'll have to modify these dynamics. Well, first of all, you know, for this Newton-like approach, we'll consider this PT inverse. And so what is that? It stands for positive definite truncated inverse. I'll talk about that shortly, what's going on there. And then distribute these dynamics by reformulating that problem again and introducing an auxiliary variable. We also have a deterministic annealing approach, which I won't spend too much time talking about. But what it does allow us to achieve is that we approach using deterministic annealing feasible binary solutions. Without this annealing, we'll actually just approach solutions that are close to the corners of the unit hypercube, but this allows us to actually get all the way to those feasible solutions. So in particular, I'll talk about two algorithms. Newton neural net C, standing for centralized. So our result here is that we converge to a local minimizer of this energy function with probability 1. That last part is also sort of a contribution over literature. These Hopfield neural networks, it has not been established that they converge to minimizers, only to fixed points. And then the distributed version of this algorithm. And so we'll have some additional analysis for once we introduce that auxiliary variable. So here I have to introduce this energy function, and we have what I call a stabilizing learning term here. So it's just the cost plus this stabilizing learning term. And this will make a little bit more sense shortly when I sort of relate this to the classical Hopfield dynamics, but just know for now that this G function is exactly what I talked about before, this sigmoidal activation function. So what I'm going to show now are some dynamics which are very complicated looking and have a lot of terms, but we're going to walk through each of those terms and factors slowly, step by step, to sort of see where the original Hopfield neural net dynamics come from, and then what our modification to those is. So here it is. I warned you, these dynamics are pretty complicated looking, but let's kind of consider slowly, each of these factors, what is going on here. So in particular, what I've put a box around here, if you consider equivalent dynamics in U, and notice that X and U, according to this function G, have this sort of bijective relationship, right? So we can consider just some equivalent dynamics in U, which are much easier to state. And these are just the negative gradient with respect to X, but when you write it in terms of U, you get a much more concise way of representing it. And so in particular that, well, actually, let me step through these terms then one by one. So these Wx plus V just come from the gradient of the cost. This term here is what we get when we map those dynamics, the linear stabilizing term, the minus U over tau that you saw in this case, right? You notice minus U over tau. That shows up from this stabilizing learning term in X. So because, this transformation is a little bit complicated, that's why it looks a lot uglier here, but we're really interested in just studying the equivalent dynamics in X. And then in particular, this matrix is just sort of a chain rule conversion when we go from U dot to X dot. So all of that was, what we're sort of building off of. This matrix out front here is this PT inverse that I mentioned earlier. So in particular, we'll consider the Hessian of the energy function, and we'll do an eigen decomposition on it and truncate the eigenvalues at some positive parameter M, and then we do the inverse. And the reason for that is, the Hessian could be indefinite if we allow this thing to be non-convex. And so if we have some negative eigenvalues, those will actually induce stabilization towards the saddle point. We don't want that. So we truncate them at some positive value to retain the property of, going towards minimizers. And also to ensure that it is not, too close to some singular matrix. Okay. So a discussion about the equilibria of these dynamics, because the dynamics look very complicated, but we can learn something from just sort of reasoning with actually the coefficients of the cost function. So in particular, what we'll actually want to do is design the cost to be very concave if we can. So what I've plotted here is 3 different cases for this coefficient of our costs, A, in the one-dimensional case. And you'll notice on the left-hand side versus the right-hand side, the gradient and the dynamics are the same in sign. So when you see the gradient flip in sign, the dynamics will also flip in sign. And that's important because we notice here in case 1, this is sort of the actually, we haven't designed our cost to be concave enough. And so we actually are stable towards the center here, towards 0.5. So you'll notice that, if I can bring my mouse in here, hopefully you guys can see this. So on the left-hand side, we have positive values of X dot converging towards 0.5. On the right-hand side, we have negative values of X dot. So this is a stable equilibrium in this case. We don't want that. What we want is for our cost to be very concave, so we're actually falling down, the level sets away from the center of the unit hypercube. And so that's what we get when we've allowed A to be sufficiently negative here in case 3. We actually have anti-stability from this point in the center and stable equilibria closer to the corners, of the unit hypercube. In this case, just the 0, 1 values that we're looking for, right? Okay. So then, we have 2 lemmas that we require in terms of actually establishing our main convergence result. First of all, these equilibria are finite in the n-dimensional case, and also that this open hypercube is forward invariant. We don't escape it or even, get to, for any positive t over tau parameter, we don't actually approach the 0, 1 corners. We approach possibly just some equilibria that are close to those. So then what is our main theorem for this centralized Newton neural network? Well, we need that the initial condition and that these t, tau, temperature, and time constant parameters are chosen from suitably dense random distributions. And that's really what's required to get this with probability 1 result, that we actually converge to a local minimizer, as opposed to a saddle point or a maximizer, which are also equilibria. And so the keys to that are just differentiating this energy function, LaSalle principle, and then in particular applying the stable manifold theorem and examining the real parts of the eigenvalues of the Jacobian of the dynamics. There's some additional analysis that's needed there to justify that we'll never, with probability 1, I should say, we won't converge to a saddle or a maximizer. Okay. So then the distributed reformulation of this will just introduce this sigma parameter, which is a vector, and I've introduced it via this auxiliary variable y now that shows up using our friend the Laplacian matrix. And so you'll notice if you multiply sigma from the left by vector of all 1s, in other words, if you sum up its entries, we obtain that original matching term that we were interested in before. And so this f tilde now, being a function of x and y, sort of captures the same flavor of problem that we had before. We can actually show that if x star solves this distributed reformulation, then it is also a solution to the original reformulation. So really we're not losing anything here by introducing this auxiliary variable. Okay, and we also still have lemma 1 and 2. We'll need those for proving that this thing converges. Okay, so some more math here, but all I'm showing now, the main thing to focus on is that this W tilde is now a diagonal matrix due to this new cost function that we've come up with. The energy function is the same exact thing as before. We just have f tilde instead of f. And so now we have these dynamics, again, very complicated, but you'll notice the x dynamics are the exact same type of PT inverse modified Hopfield dynamics, where now we have W tilde and V tilde, which induce our distributed structure that we need. And H in particular will also be a diagonal matrix. So it's much faster to compute that PT inverse now. And then Y dot is just going to be gradient descent on that energy function. And so I've written out exactly what those terms are, but the important thing is maybe just notice that we're descending just in gradient on that energy function. Okay, we do need, quick remark, 2-hop information to compute this Y dot because L appears twice in this equation. We lose the squared nature of the penalty if we want to design a 1-hop algorithm, but that is doable. We could just consider a sort of a linear nature of the penalty term instead if we wanted that. So, okay, analysis, pretty much the same assumptions as before, except now we just need that the graph is connected, right? And we have the same sort of result. We converge to a local minimizer with probability 1. And in particular, our Y star will actually be optimal with respect to any fixed X star. And the intuition for that is this energy function is convex in Y, right? And so the important parts here are mostly just reasoning with this auxiliary variable Y, and then using the same results as before. Okay. So in terms of trajectories for this, so here this sort of demonstrates moving these stable equilibria closer and closer to the corners of the unit hypercube, to feasible points, that is. And so that's done by updating this t over tau parameter online. So you'll see each x marks an equilibrium, actually. And so those equilibrium shift closer and closer to feasible points via this deterministic annealing strategy. You know, we find that we're much more scalable, particularly way more than SDP relaxations. You'll notice the brute force approach to this just blows up that black line on the left-hand side of that graph. So of course, that's not even suitable for any problem size greater than 20 or so. And then, you know, we notice that the distributed version of this is actually a little bit faster than the centralized version. The reason for that is the PT inverse is again done on a diagonal matrix now. So that's very quick compared to doing a PT inverse of a fully populated matrix. And then the table on the right-hand side here, just briefly what's going on here is I ran a handful of trials, and you can think about this Q scores as if a method achieves the best possible performance in terms of the cost that was obtained of the solution, it'll give a Q equals 1 in every, you know, if it achieves the best in every instance. Otherwise, you know, if it's the worst in every instance, it'll achieve Q equals 0. And so it's maybe not immediately clear here. We do notice that the tried and true methods of greedy and SDP perform a little better in terms of that solution cost. But what's baked in here that may not be immediately obvious is our Newton neural net D/deterministic annealing. That approach actually does beat both the greedy and the SDP approaches in, I think, 7 or 8 trials or so out of 50. So we're not hopeless. We actually do better than it sometimes. Okay, so we have, you know, a publication on this, which will appear shortly in Automatica. Again, it'd be interesting to much more closely analyze those deterministic annealing dynamics. And in particular, maybe obtain a theoretical guarantee. If you do it slowly enough, you might be able to achieve that this approach is a global optimizer. And then just sort of extending the approach beyond this context. So I notice we're at 10:50, so I can maybe take about 5 minutes on these additional topics or less if we need to.
Yeah, so Tor, maybe you can go directly to the demonstrations. I mean, the more the application part, and explain our, you know, the project we worked on. And by the way, I didn't mention at the beginning of the presentation, but Tor, and also Priyank, I think he's here. But Tor, you know, helped a lot in implementing algorithms like the ones he presented on campus on real loads. So maybe you can go ahead and explain.
Yeah, sure. So these demonstrations that we've been doing, or that we started a couple years ago, is what I'm going to talk about now. So we consider just sort of a problem formulation. This is actually exactly the same as the first formulation, the convex case that I showed before, BDP-B. So we're interested in solving this optimization. And in particular, we want to address some current challenges for renewable energy integration. You know, some of those issues that I presented on the motivation, the very first slide. But issues are that the current demonstrations that are being done on this, the state-of-the-art work, is either very small scale or is homogeneous in the sense that the population of devices they consider is, for example, all electric vehicles or something like that. So we really wanted a larger, more heterogeneous demonstration of solving instances of this PDFR and then dispatching those solutions to real physical devices. And so I'll briefly touch on our communication network here. What we have in the center is the cyber layer of what we implemented, which is a Raspberry Pi network that was using distributed algorithms to solve instances of that PDFR problem that I showed on the previous slide. And then this communication network dispatched solutions to air handling units, V1G and V2G electric vehicles, meaning vehicles that only charge or vehicles that can charge and discharge to the grid even, and also a lithium-ion battery that was connected to the UCSD microgrid. And so then the thing I'll highlight here is just that we had to deal with different signal update times for each type of device. You know, the V2G EVs, for example, could update very fast on the order of 1 second. We had some slower responding devices, such as the air handling units. We could only update every minute. So sort of thinking about how to accommodate those slower update times in our algorithm approach. And we had, on the order of upwards of 60 and upwards of 50 devices for our real tests 1 and 2 here. And so then what's actually the outcome? On the left-hand side, I'll just briefly comment that these are kind of the, what we expected to be the worse implementations, the earlier on before we had some lessons learned about what was going on here. So for example, this top graph on the left, this was for air handlers in our very first test 0, and it looks like total crud. This was not really acceptable. We weren't going to get very far with this. So using, thinking about how we could actually activate or actuate these air handlers in a more intelligent manner such that we can actually demonstrate some load following achieved, the top graph on the right-hand side here. And then finally, I'll note, the total response for test 1 is the bottom graph here, which, we sort of closely started to match that. But again, due to some improvements on our actuation schemes, we did a lot better with the total response, which is shown in the bottom graph on the right-hand side here. And so then, the outcomes of this are that we did some economic benefit. UCSD could really benefit just from using this population of devices. We're eligible to participate in the market. In particular, we computed their market score, and we exceed the minimum score that we need to participate. And so this helped us procure a DR Connect grant, which in particular, the future directions on this is that DISCRN project will aim to expand this test bed so that it's more available in sort of an open source sense to be available for researchers to test distributed algorithms on real physical devices. And so, I'll just note finally that validating these algorithms on real physical systems is really the most important thing in terms of moving towards widespread adoption of these things and enabling more renewable energy resource penetration in the future. And so that's it. So thank you, especially to all my collaborators on the top row, and some friends and family pictured on the bottom row. And I'm happy to take questions at this point.
Okay, thank you very much. Virtual round of applause, I guess. And so now we are going to divide this in two. So first, the audience can ask any questions about what you've seen. And then actually the committee and the candidate are going to then separate and have a discussion, behind doors, I guess. So, okay, so please go ahead, ask any questions. If you want to use the participant, you can raise your hand and in the participants, right, list, and I can give you, I can let you speak or, yeah. So are there any questions?
Questions in the chat might work as well, if that's easier.
Questions in the chat.
So I see Ben is raising his hand.
Okay, Ben, go ahead.
Hi, hey Tor, nice present. I was wondering for the for some of these practical implementations, do you have everything, like if you're trying to branch these out into other power networks and you want to have a way to generalize your methods, how much do you require additional modifications to any of these systems, or is everything already good to go? Like, do you require additional sensors, or do you can you kind of plug and play into existing?
Yeah, good question. So I think it's sort of, well, the basic answer is yes. If you're going to, it depends on how you model, the decision-making devices, the agents with autonomy over the system versus the actual generators. So the way I posed it in the theoretical portion of the talk was that possibly every single generator or load or device is actually an agent that we model in the system. And then, we assume they all have microcontrollers or something, they're smart devices or whatever. But in implementation, actually what you'll notice in the communication architecture is we only used 9, I believe, decision-making nodes for a population of upwards of 60 devices. And so that's because we did some aggregations. So we actually computed solutions that were sort of aggregated solutions for a population of electric vehicles, let's say, and then sort of had some more localized logic to actually implement the control actuation decision there. But then in terms of sensing, yeah, I mean, because what I've shown here is actually not really an output-based, feedback type of controller. But if you are going to implement some, more localized control, of course you'll want to have some sort of sensing information. But really, it just depends more about in terms of the formulation that you're trying to solve. That will directly tell you, how much information you need. Does that kind of answer the question?
Yeah, thank you.
Great.
Okay, great. So Patricia has a question.
Okay.
Yeah, thank you for the presentation. It was really good work, and I'm excited to see the outcome in the end. I had a general question when it comes to the implementation as well. In the microgrid, do you see like challenges in implementing because of transmission constraints, or in the microgrid it was mostly fine in terms of capacity limits?
Really good question. And so that sort of exposes, sort of an oversight, an intentional oversight, but something that we sort of relax in the formulations that we consider, which is that there aren't these transmission type of physical network constraints baked into the formulations that we consider here. These formulations in this talk are more about the cyber layer decision-making part of the system, but and so in particular, for these real demonstrations on the UCSD microgrid, because we were dealing with a small enough population of devices, we just figured, okay, we can turn off air conditioners. However, we actually did this in the middle of the night, so we weren't messing with, lecture rooms during class. But yeah, so it wasn't really on the scale that we'd have to worry about transmission constraints, but that is, something that both needs to be considered in sort of the full, most rich implementation of this in the near moderate future. That needs to be considered, and also that it can be, that there are approaches to these types of things which do accommodate load constraints. I can think of some ways that you would modify some of these algorithms such that you're additionally satisfying power network constraints. So yeah, good question. Thank you.
Can I ask a follow-up
Sure.
on that? So I think you probably had communication delays. Do you have to change your algorithms to adapt for that?
So in terms of the decision-making cyber layer of the thing, what was going on inside this dotted circle here, we encountered, just some issues in terms of getting agents to agree on the iteration step that they were on. We don't want any one agent, if we're doing this just via an Ethernet switch that are exchanging data as quickly as it can, that's not really, we have to build in some synchronicity into that. And so, that's just done sort of via some logic, getting agents to agree that they're all on the same iteration before incrementing the step. So that slows down the real-time nature of it a little bit, but things are happening so fast that it's still very fast in real time. And then in terms of communicating those signals to the real devices, yeah, we didn't really need to worry so much about delays on that front. Yeah.
Okay, thank you.
Sure.
Okay. Are there any other questions from the audience? I don't see any other hands. So, okay, so I guess that, yeah, we'll stop here. And now all of you, all of the audience, you have to leave and leave us with Tor so that we can ask him more questions.
Great. Thank you, everyone, for attending. Appreciate it.
Yeah, thank you very much.
Thank you.
Bye, Mom and Dad.
See you in a couple weeks.
Sure. I'm going to use the restroom briefly, if that's okay. Just as
That's
we're
okay,
kind of
yeah.
waiting for people to filter out here. Okay, I'll be back in a minute.
Yeah. Yes, so Benjamin, you're still there. And Hankao also. You will have to leave.
You need to kick them out. Maybe they fall asleep or something.
Maybe they first, yes. Yes. Well, one of them at least asked a question, so he woke up in the last part.
As we wait for Tor, if you don't mind me using this opportunity to ask Behruz, back to the topic that I mentioned about COVID, a COVID workshop or seminars and so on, which Sarah Javidi, in her academic senate role, mentioned to us. There is a meeting today at 3 p.m. of various campus researchers working on COVID-related issues. And it would be the ideal time to continue this discussion about seminars or a workshop or a few very brief workshops on subtopics. Would you be interested to take part in that?
Oh, sure. If I have the link, I'll try to join. Yeah.
Wonderful. Thank you so much. I'll have the Zoom link sent to you.
Thank you. Appreciate it.
So Tor, I think you are recording this. I think it's better that you stop
sure.
the recording.